call is now being recorded.
Okay. In this video clip, I would like to explain two common program types. That is linear program and quadratic program. But let's see. I think maybe we can finish only linear program. By the definition, a linear program is a minimization problem of linear objective and linear constraints. That's the whole idea. We already have we have seen that a linear function is in a general form is expressed as an inner product of a constant vector and your vector x. Okay. For constraints, we have two types of constraints, right? Linear inequality and linear equality. So depends on the size of G. Actually, this is a vector notation. What it means is that you have G1 transpose X less than H1 and GM transpose X less than HM. Okay, by this notation. What is GI transpose? GI transpose is actually the ith row of G. Okay. So by the syntax, your vector H has to be a vector of m by 1. Okay, this is just to explain the notation. Linear inequality, okay? And then for linear equality, so if A is P by N, this equation say you have 1 transpose X equals B1 and A P transpose X equals B what? BP. Manosha, how many inequality constraints? Inequality constraint. M. How many equality constraints? P. Okay. Okay. So the whole idea of linear program is minimize linear objective with the linear constraints. For example, when your x, you have questions? Have questions? When x is a vector of n by 1, let's say x is a quantity of different foods. Each food has a cost of C. Suppose you have food 1, food 2, 3, dot to n. Suppose your food 1 is burger, okay? Food 2 is soda, which is not very good. Rice bowl, for example, all right? Of course, each food has a certain cost. This is what, 200 baht, right? 15 baht. Rice bowl is 200 baht, for example. Each kind of food have different portions of nutrients, right? Burger has this percent of carb, this percent of fat, right? So on. And then if xj is going to be a quantity of the j food, which means how many burgers should I have, how many rice bowls should I have. If 1 unit of food gives you a certain portion of nutrients, okay, what? So Dij, we come up with a notation Dij. Dij is going to be the amount of nutrients I that you get from food J. So the nutrient, it can be something like I say carb, fat, what else? Vitamin and so on. Okay. So when you want to decide about the food, like the diet plan strategy, what's your goal? Your goal is maybe the goal is about the cost that you want to minimize it. But the constraint will be something like, if I eat that kind of food, if you don't care about the constraint, you end up eating garbage food, the cheapest price, right? But the cheapest price, of course, will not give you enough and healthy nutrients. So that's why the constraint would be like oh, dx is greater than h, that means the nutrients 1, 2, 3, 4, 5, right? The numbers of row in D must be greater than a threshold h, all right? And the quantity should be non-negative. Okay, simple questions. You wanna, this is a cost objective, and you have two constraints. Bunyarit, can you express this as a standard form? What is G and H, A and B? Do we have equality constraints or not? We don't have equality constraint. We have only inequality constraint. What is G and H? You have two inequality constraints, right? Two sets of inequality constraints. How can you combine them all into a single vector form? So G gonna have two portions, right? Two portions as two row partitions or two column partitions? Two column, like how? Like this? But I mean, G has to be multiplied with X, right? So Manosha think is two row blocks or two column blocks? Two row blocks. Minus D and let's see if maybe X less than, right? Can you feel it on the left hand side? Minus D, X less than, what is this thing? Minus H, right? From here, minus H, minus I, 0. Okay. This is maybe this is a constraint from your problem description when you formulate the problem. Now, it should be very simple process that you put your problem back to standard form. From this format, this is going to be your G, right? Okay, this is going to be your G. This is going to be your new H. When you solve a linear program, just again figure out the dimension of G and H, because that tells you how many linear inequality constraints you have. And again, I don't want to swap the screen again. When you have a linear program, you have a dedication for linear program. Okay, so it's your job to recognize what G and H and A and B and C is, and just put it back into the command. Okay, now we have to we have really when we have a linear program, because it's a linear function, it's always nice to understand the interpretation of linear function and something related to that. When you have a linear equality, that is a hyperplane, right? If I change equality into inequality sign, what does it mean? I have hyperplane on this space. This is AX, A transpose X equals B. If I put it into inequality, what is this region? Under or upper hyperplane? What does she say under, Rachan? Is it not an area? You should say it's a region, okay? Under, okay. Obvious, right? Is it obvious that it's under? So there's going to be two sides of the hyperplane, upper and under, all right? Because this is inequality constraint. That is the region under the hyperplane. Okay, both upper and under the hyperplane, we call it half space because it's a hyperplane divided space. Like the hyperplane divide the Rn space into two halves. Okay. Okay. What happens if you have bunch of inequality constraints? Comma means and, right? And this X has to satisfy this and satisfy this and satisfy this. So it's intersection of a lot of half spaces. Tung tung tung. Okay. If I draw it into R2 plane, one hyperplane is this line, right? The half space, one half space is going to be this. If I have another hyperplane and if I have inequality, so it's going to be another half space. After I intersect all of them, it's going to look like this. It is called a polyhedron. I think this is a singular form. I'm not sure if it, like you have polyhedra. I think this is plural form. Polyhedron is singular. So because linear program always consists of linear equality constraint and linear inequality constraint. For linear inequality constraint, the constraint set looks like a polyhedron. A polyhedron, so you will never have a constraint set of linear program that looks like have a smooth surface, right? Always polyhedron. Good exercise. The very first thing, the basic skill that you should develop when learning a linear program is that to understand a simple linear program graphically. So this is only feasible for a problem with two variables. Now let's take a look. There's going to be two LP. Those two LPs only differ by this inequality constraint. Now let's take a look at the first one. X1 plus X2 less than 6. Okay, that's this curve. If I have inequality, which region? Nacha. Below or upper the orange curve? Below. Okay, the second one, X1 minus X3 is this curve. I have inequality. Nalidom. Upper or lower? Huh? This side or this side? One or two? One. Okay, so we have boop, 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 boop. The third one is x1 plus 3x2 greater than 6. The green curve. Region 1 or region 2. Next to Warachit, what's your name? Pachanon, region 1 or region 2. Greater than 6. How do we decide? Let me. Can I ask? How do we decide which region? One, right? You just notice at the origin, right? Like when you plug the origin back, does it satisfy the constraint or not, and decide. Okay, so it should be region 1. I'm going to erase. If you intersect all of them, how do we get? How do we get? So you're going to get this one, right? Now, if you move to the second problem that I intended to be the similar LP, except that it has extra conditional, sorry, not conditional, like extra non-negative constraints. So for the second LP, the constraint set would be is it smaller than the first one? Like how? So it's going to be this, right? Okay. Now I'm going to erase. I'm going to erase. Now, for symbol LP, okay, for the first one, pay attention. Remember the concept of having the level set and the constraint set, right? The solution of your optimization has to stay in the constraint set. So obviously for LP1, it has to be inside this polyhedron, always. And now we're gonna examine what the level set look like. And then the optimal solution would be the point where you stay on the constraint set, but it corresponds to the smallest function value. First one, I'm not gonna do all of them, all right? This is very simple. Optimization student. อะไรอ่ะ บุญยฤทธิ์ or ราชัน how many only you two or บุญยฤทธิ์ if my C is vector 0 1, what my level set look like? How does my level set look like? The function f is linear, right? Is linear. We have talked before, when you have a linear function, level set is, how does it look like? A contour. It's just a line, right? It's just a line where the normal vector is no. I mean, remember you have a contour, right? If you look at the surface, right, the gradient has to be perpendicular to the tangent surface. But because it is linear, obviously, C is a normal vector to that linear or the hyperplane. C is 0, 1, right? And for linear function, the vector C is served as the gradient vector as well, which means C is pointing toward the direction where f is increasing. 0, 1. My level set is going to be a line, right? Vertical line, horizontal line, or tilted line. บุญยฤทธิ์ horizontal line, vertical line, or something tilt. C is 0, 1. Where is the direction of 0, 1? Zero, 1 vector is this or this. It's a vertical vector, right? So my level set would be horizontal line, right? My C is pointing toward that way. I zoom up. All right. What do we find in this linear program? Again, my solution has to stay on the constraint set, has to lie inside or on the border of that polyhedron, that thing. But I'm gonna look at the point of that polyhedron where it corresponds to the smallest function value. The horizontal line, the smaller value, the higher or the lower, right? Because my gradient is putting that way. Solution is the blue, the green, the red, or the yellow. The yellow. Okay, you just look at the coordinate. We're not gonna do all of them because this is a very basic, right? Maybe so sorry, I think I draw the region incorrectly. Previously we talked about LP1, right? The LP1, the constraint set is this. Sorry, but that doesn't change the solution. Now still stick to the LP1. For LP1, for C, right? For C this, you say that X star is a yellow point. My message is observe that your constraint set is unbounded. Understand? Unbounded set? Because I mean, it's unbounded set. It means that there's members in the set that that has infinite size, infinite magnitude. Your constraint set is unbounded, but when C is that direction, your optimal solution is attained and given by the yellow point. Your P star is finite, right? Now C is what? What about C is -1? Maybe no. Okay, I want you to do all the exercise in this, but maybe I give C is 1 and 0. C 1 and 0. What are the vertical? Sorry, what are the level sets? No, no, นัชชาแล้วใครนั่ง next to นัชชาสาลิตใช่ไหมสาลิต what the level set look like 1 and 0. So the level set is still going to be a line, right? Vertical line, right? Vertical line. The gradient, the vector C is in 1, 0. Left or right, the vector C is pointing toward the right, right? So smaller the function values, the further left you move. P star is, where is the solution? P star is minus infinity. All right, your problem is unbounded below. Understand? Again, all right, as I said several times, when your problem is unbounded below, it's just meaningless to solve the optimization problem, right? Yeah. Can you do the rest? This is not difficult. Maybe with the same question, right? With the same question, C is pointing 1 and 0. But then now I want you to take a look at LP2. Now the constraint set would be this, right? LP1, it has unbounded constraint set, but LP2 has a bounded constraint set. With the same objective, with the same objective. Now, what is my P star? My C is pointing that way. Maybe take a look at the X star first. What would be the optimal solution? We should pick the green line that is toward the left, right? But still has to intersect with the constraint set. Which line? 1, 2, 3, 4, 5, 6, 7. The fifth line, right? But the fifth line, the X that stays on the constraint set, where it still correspond to the fifth line, bunch of them, right? The bunch of them, because the constraint the boundary of the constraint set happen to be the vertical, like the vertical line segment as well. So all the points on this line segment are optimal solution, which means optimal solutions are not unique, but it would attain to the same P star. That is calculate. P star is 0, because it's C1 x1 plus C2 x2, right? All the points on this line segment, x1 is 0. Okay. Can you do the rest? Can you do the rest? All right. Which means a simple linear program like this, you can just recognize the solution. Um, now, if I ask you like a reverse question as well, usually when you solve an optimization problem, like all the problem parameters are given. Like they give you C, A, B, and everything, right? And then you solve for optimal solution. Now it's a reverse question. If that happens in engineering as well, all right? Um, if I want my optimal solution to be the red one, what would be all the possible vector C that would end up having the optimal solution on the red point? Understand the question? Okay, so let's just exercise. All right. There are some example in the questions as well where you as a user, I think you have a choice on choosing the vector C in this case, and now you wanna manipulate or decide the vector C so that your solution end up here, things like that. We're gonna finish. We're gonna be finishing the LP. This is some conclusion from the theory of LP. Unfortunately, we don't have the time to all of them. Let me sketch in real quick that you're gonna have another standard form of an LP. Okay, the standard one that we see is minimize C transpose X, and then you have linear inequality and linear equality as a separate set of constraints. This standard form can also rearrange into a single linear inequality, but with the non-negative constraints in X. There's going to be a technique, but using the idea that any real number can be split as a positive part and the negative part, all right? And the inequality constraint can be make it up as equality by adding a slack variable. บุญยฤทธิ์อะไรนะบวก s plus s you add a slack variable, but with this s, now this s has to satisfy some condition. If this guy less than 3, so it means that you must add up some quantity. That quantity is non-negative, right? So this is kind of a like standard technique, which means you can always translate inequality into equality, but there's going to be slack variable that are introduced. Okay, don't worry about that. We're not going to go to that because I mean, as this step, we're going to just call the available tools, and all of the available tools both in MATLAB and Python rely on this standard form. It's just a matter of when we learn the simplex, like a particular algorithm, that they rely on that standard form. Last, can I do real quick? There's there's a result that, can you imagine when you have constraint set that look like polyhedron? Okay. If I choose C like this way, if I choose C this way, right, my level set is going to be like this, right? The optimal one would be here, right? If I choose C that way, my level set is going to be this. My optimal would be, yeah, either on the boundary or like it depends on the direction. Are you convinced that the optimal solution never stays inside the polyhedron? Do you agree? It never stay inside like interior point, because I mean just come up with any direction of C, right? Or maybe C are in this direction. If C is in this direction, the level set would be this, and you end up here, right? Oh, we talk about let's just assume that we talk about the polyhedron that is bounded. Okay, just talk about the bounded case. So this is one important property of an LP. Okay, Rachan, maybe you can wrap up. The solution of LP. This is like the idea of simplex method as well. Yes. Solutions of LP stays on vertices of polyhedron. I mean, we talk it in general. You may say, oh, it could appear on the boundary as well. Yes. What I mean is that the optimal solution is never on the interior point of a polyhedron. Ah. Last, I would like you to learn about this standard technique. Okay, standard technique. For this slide, can you maybe just take a look? I may have assigned as a homework as well. Maybe the homework is this. This is homework 4, all right? Homework 4. When the constraint set of LP is simple enough, you don't actually have to solve LP at all because it has a closed form solution. One of the obvious constraint is called a box constraint. Again, I illustrated with R2. A box constraint means you have upper bound and lower bound on X. Okay, box constraint. If my C is this, where my solution? Any point on the lower bottom, right? If my C, the, how do you call it? Lower left corner. If my C is this, upper left, right? Okay, so it seems that so my C is 3 and minus 2. Which way? What is the quadrant of my C? Where is my C? Quadrant 1, 2, 3, 4. 4, right? If my C is that way, my solution is in upper left. Now, can I conclude that in general? I have given you a vector C in R2, C1 and C2, all right? So it seems that, oh, you have a very deterministic rule, right? I mean, if C is a vertical vector, solutions are not unique and given by this, right? But if C is slant in the first quadrant, how can you explain vector in the first quadrant? Yeah, so the constraint would be if both C1 and C2 are non-negative, the solution is lower left, which means what does it mean? Lower left? Where is it? You have these as problem parameters, right? L, which L? L has L1, L2. U has U1, U2. Where is this point? L1, comma, U1, right? Just that. So solution is L1, U1. เฮ้ยเอ้ยเดี๋ยวก่อน L1 L2 okay so L is a lower bound right L is a lower bound in x1 direction and in x2 direction can you do something like this now when you get into R2 if you finish the R2 case can you extend into Rn case Rn C1 like your C is C1 C2 dot Cn ah does it matter about the sign of L and U I mean the sign of L and U can be mixed can be both negative and non-negative got it like L can be minus 1, 2, 3, 4, right? U can be 5, 3, and then 10. Like the sign can be mixed in the vector L. Okay, that's it. Last thing, all right? Exercise, this is your homework question 4. Can you write a general solution? So it means that when you end up having LP, simple LP like this, do you need to call a solver? Do you need to call a program in order to solve an LP like this? No, right? It has a closed form solution. We have another examples as well. There's a bunch of LP form that already have closed form solutions. Last one. Emo. 10 minutes. Some problems may not look like an LP, but it can be arranged as an LP. Remember that we explained at the beginning that LP is just a problem of minimizing a linear objective. So you may think that if I have non-linear objective, then it cannot be an LP. But okay, we have some example. The norm function is the norm function linear? No, right? Obviously, the norm is non-linear, right? Because the norm, right? Norm satisfy triangle inequality. It doesn't satisfy with equality, right? Right? What do we have? Any kind of norm would satisfy with alpha 1 x1, right? Plus absolute of alpha 2 x2, right? So it cannot be linear because in order for it to be linear, these would satisfy with equality. So the norm, any norm, one norm, p norm, infinity norm is not a linear function. So but for L1 norm and L infinity norm, it has a certain mathematical property. Okay, now this is a standard technique. So this is a problem in application where you want to find again a linear model that approximates G, but the way you measure the error is you're gonna try to use L1 norm instead of 2 norm. All right, mean absolute error. That's what it means. At the same time, you have constraint on your variable x. I don't want my linear model parameter to be large, and by that, I use infinity norm because that means that for all entries of my x, each entry of my x, the magnitude cannot be greater than 1. All right, that is a motivation for my application. Let's just say, all right. So that's why I use the infinity norm. Okay. Then again, obviously, and at the first glance, this is nonlinear objective. This is nonlinear constraint. But okay, we're gonna use equivalent condition about this L1 norm and L infinity norm. First of all, if you have everyone knows that the one norm of y is what is a summation of yi, right? It's a summation of yi, right? What happened if I first of all I say what I want to minimize the L1 norm, right? Then maybe I introduce a vector u first. I introduce a vector u. So, oh, sorry, not in this slide, all right. In this slide, I use for example, okay. Let's say, okay, maybe just see, follow the slide. Fx minus g is going to be a vector. If I put upper bound and lower bound like this is equivalent to the absolute value of this vector less than u. Now I use the absolute value as a element-wise operation. It means that it returns the vector of absolute of each of all entries, right? I mean, they are equivalent. And agree? Okay. Then if I enforce that constraint, my L1 norm, which is a one norm absolute value, would be less than 1 transpose u, because 1 transpose u is the sum of ui, right? Now, if I want to minimize the one norm of this vector, but my one norm of this vector, if I enforce this as a constraint, so this is going to serve as an upper bound of the sum, right? I want to minimize this one norm. I enforce this as a constraint. This is an upper bound. So I minimize upper bound instead. Does it make sense? Like you have this function, you have an upper bound for it. All right? You enforce this relationship upper bound to be maintained. And then you try to suppress the upper bound. Right? And then eventually, if it's possible, you're going to end up at the minimum. Which means now you have introduced one additional variable u. Okay, u is served as an upper bound of the absolute value of this vector, and your cost objective, which is one norm, now you can express it as a linear function in u. We almost done. How about the infinity norm constraint? If infinity norm of x is less than 1, it means infinity norm is what? What is the definition of infinity norm? Maximum of all xi, right? Right? Infinity norm. X is minus 5, 3, 2. Infinity norm of x is 5, right? Infinity norm of x is 5. Is the maximum magnitude of all entries. Then you see that because of the definition of infinity norm, if infinity norm is less than 1, like the largest magnitude is less than 1, so all the entries must be less than 1, right? It is equivalent, right? One important fact, when you have constraint functions and you want to derive another form, another expression of the constraints, another form must be equivalent. Cannot be less restrictive, cannot be more restrictive, because that's going to end up having bigger and smaller constraint set, right? So this is a process of deriving equivalent constraint. Now, if I use vector notation, the magnitude value of vector x is less than 1, right? This is my notation. I use like inequality sign that looks very curly. That means a vector notation. It means that it applies to all entries in the vector. So magnitude of x less than 1 is going to be the same as x is less than all one's vector. Rashan, ready to answer. Okay. Now, what are the variables in the new formulated problem? Variables are u and only u and x, right? Okay. Can you recognize, is this a function of, what kind of function of your new variable? My new variable is going to be x and u, let's say x and u. The cost objective, 1 transpose u. Your new variable is z, right? Your cost objective, is it linear in z or not? If it's linear in C, you must be able to express it as something transpose constant vector times Z, right? Is it linear? A linear function in the variable? Linear. Okay, what is the vector C? Rashan. It doesn't involve X, right? It doesn't involve X, so this portion is 0. What about the bottom part? 1. So this is your new vector C. Okay. Now, is this linear in the variable? Next. Now, if you take a look, all of these are inequality, are linear inequality. How can you recognize this is linear? U, right? It contains only linear function in U, linear function in F, linear function in X, sorry. All right? Once you detect that, oh, it's all linear function of your variable, then you say, oh, turns out that it's a linear program. Originally, it doesn't look linear at all, right? But with this standard technique, it can be formulated as a linear program. Uh, at the end, the homework, maybe no, because it's too easy. Now, can you answer and then we are done? Can you answer and then we are done? I want to formulate it as 1 transpose X expressed as GX transpose H. But now, in order for you not to get confused, I'm going to use Z, right? Because it's a new variable. Z is X and U. Now, we previously, our C is what? 0 and 1, right? Now my G. Now G. Because your Z has 2 partition, you have, a lot of constraints. So first of all, I mean, the number of column block in G should correspond to the variable set, right? So it's X and U, which means you're gonna have like 2 portions, 2 column blocks, and then the number of row blocks in G should correspond to the number of constraints you have. Maybe we do it one by one. I'm gonna take a look at this side of the constraint. Hurry up. This side of the constraint, can you represent it as one single constraint? It's gonna be minus fx minus u less than g, right? Can you fill it in? Bunyalit, first row. Uh-huh. Oh, u is a vector. Huh? Is a vector 1 or is identity matrix? Identity matrix, right? On the right hand side is what? G. Okay. I'm gonna erase. Now. Who's gonna answer that? Peter Pong. Is fx minus u less than g? So can you fill up? F. Okay. There are two more constraints. This side, Zen, can you flip the sign? No, minus x minus 1 less than 0, right? Can you fill up? So I'm gonna add two more rows. If it's minus x, like this portion will be multiplied with x, this portion will multiply with u, but it has a function of x only. It's minus x, so this portion would be minus I, and the second column would be that there's no u, so it must be 0. On the right hand side is 1. Sorry, I should have moved this. All right. The rest ใครล่ะนฤดม the last one I 0 1. Okay, and that is going to be the vector that you put into the solver, right? We have got the vector c, we have got the inequality constraint. Okay, if your math is correct, if you understand the syntax, if your x last thing my f is m by n, my x is always n by 1. What is the size of my z? Z. My z is x concat with u, right? My x is in Rn. What about my u? U is an upper bound of this vector. F is m by n. M by n. So my x has size of n. What about my u? M. So your new variable, m plus n. How many constraints? What is the size of my g? Oh. This is m, this is n, right? For what about this I? What is the size of my I? Oh. Yeah, but you already know that u is an upper bound. Yeah, m, right? M. M. So this is another m rows. What about my I here? What is the dimension of my I? N. So you have 2n. Yes, done. Okay. Why is it important to like figure out this? Because when you code, you're gonna code like, you're gonna construct this array, right? This array as a partition of different things. Just figure out on the dimension correctly, and then it's done. Okay, that's about the LP. So in conclusion, when we understand an LP, when we learn about LP, I hope you recognize a problem into LP form. And then for simple LP, if it can be described by the graph, you can characterize the solution graphically. ตกลงรู้กันบ้านแล้วนะแปลว่าไปทำ